going to do our Fourier series for the discrete Fourier transform example that we did previously. So let's go back to our Mathematica notebook. And last time we produced this really nice frequency spectrum, and we learned about the Nyquist frequency here. This is kind of plotted basically fully to length of an. So again, you see this kind of mirror symmetry, but again, we know that we want to plot only to our Nyquist frequency, so I'm going to do that n divided by 2, and that's giving me everything. We do not want to length of an over 2. Let's go ahead and change. Let's see, this guy here. And now we're basically switching to our, actually we don't want to go to 0. We want to go from I equals 1. Excuse me. This is 1, and we are not plotting the 0th order harmonic this time. Now we'll get our basically frequency spectrum that we should hopefully see in here last time. So this is just, let's go ahead and drag it to the side here. Let's zoom out. We can kind of see those values make sense. So let me zoom out here. Excuse me for the technical little glitch here. Let's put this side by side, and we could see our frequency spectrums match. So we go to our Nyquist frequency, because again, that's the highest frequency that we can resolve. Nyquist frequency is just fs over 2, and again, we're plotting to n over 2 delta f. So let's go back here. I'm going to minimize this, and let's go into calculating our harmonics on our Fourier series. So we have our a sub n's, we have our b sub n's. So in order to calculate our Fourier series, we need our a sub naught over 2. Our a sub naught is just going to be exactly this 2 over n in our new kind of summation format. So 2 over length of our data. And then all we're doing, again, we're just going to take this value here. What happens when cosine is 0? That's just 1. So to calculate 0th order harmonic, it's just going to be this. So 2 over n times the summation of all of your y data points. That's it. Pretty straightforward. Hopefully fairly easy. And so a naught over 2 would just be equivalent to, again, this total dat divided by the length of dat. So this is just kind of a quick notation here, but I can just replace this with a naught over 2 if it will make people look more comfortable. So here I'm going to take my a sub n's, multiply them out. Again, I want to do it, pull this up here, times delta f. Again, I'm rewriting in terms of this function, where we know that our delta f, as we saw last time, was 166 hertz, 167 hertz, and you can kind of confirm that. So again, I'm just taking my harmonics here, harmonic here, pulling it out from the list here, and multiplying it each time by the sine and cosine respectively, and then t times these integral numbers n of delta f's. So that's it. And I'm just plotting it to 1 over n over 2, my harmonics. So this is my y of t function. So let's see how it looks. Let me zoom out a little bit. So the red is, or the blue are my points. The red, my actual discrete data points that I've collected, as we saw last time up here. So these are my points. This is my harmonic function and my Fourier series. And here we go. So you can see it fits it pretty well. But you see there's some points that there might be some, basically it kind of misses it a little bit, not exactly on. But again, remember, this is only for, let's look at it, length of an divided by 2. So this is only for 6 harmonics. So how would I increase basically the accuracy of the symbol, or the accuracy of this approximation? Well, I'd have to increase my order for harmonics. And in order to do that, I need to increase my number of big N data points. So I need more discrete data points in order to kind of fit better, to include more harmonics. So it's kind of it's distinct, obviously, from your continuous Fourier transform analysis, but it's the same kind of principle. We need more points, we need more harmonics in order to better approximate our function. So we need more big data points, big N, essentially. So our big N that we saw last time, that's what, actually we don't have it defined in this notebook, but basically the length of our data. So let me go to the length of our dat. That needs to be increased. So if I have more data points, here I can increase my number of harmonics. So I'm always limited 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm always limited by my number of data points there, nor if I want to increase my number of harmonics. So next video, we're going to get into this concept and what we see here, this delta f being really, really large, this concept of signal aliasing. actually not signal aliasing, excuse me, spectral leakage. You're already experts in signal aliasing. So now we're going to get into spectral leakage and what can be kind of happening in this system. So I'll see you all next time. Thanks. Bye.